So artificial intelligence, a topic that gets a lot of attention, probably too much hype, and there's probably too much expected of the current models, and it won't be able to scale the way we think it can scale. And we want to give an approach that I think has much more applicability and can be much more effective. So there's some areas that I want to cover. First and foremost, we think that there's this relationship between having a lot of data and then making sense of that data. I don't think that's the case, and I think the more data we have, the more we understand those limitations. And common sense, more than anything, is being able to understand what really matters versus what doesn't. And then we'll look at what I think are some very interesting solutions and some interesting research going on in that area. And that's an area that we are following very closely and we're trying to implement. And so one of the things that we want to talk about is, well, how the brain actually works. We call it cognitive architecture, versus neural networks, which is a misleading phrase, and we'll get into the specifics of that. And then the other thing we want to cover is, the brain does what it does with very little energy. And yet we are now demanding more and more data, more and more applicability, more number crunching. And so we're spending way too much energy and not getting enough value. And I think that just doesn't scale given the current models that are being used. And that's why we think that there's a better artificial intelligence solution to discuss. So one of the things we want to talk about with big data and trying to get something useful from the data that we have. Well, first and foremost, we're being misled in essence by a term that's called neural networks because the brain works on a neural network. Computers do not. The way artificial intelligence works, you may understand this, that there are different layers to the programs, and those layers, deep neural networks, deep learning, really means that we've got one algorithm, then another algorithm, and then they kind of modify each other. They go processing and processing, and we have more and more layers. And that gives us better data. For sure, that gives us better output, but there's still limitations. Better is not good necessarily. And that's the thing we have to understand. And another term that gets tossed around a lot, which I really push against, which is called artificial general intelligence, meaning basically artificial intelligence is going to be everywhere. Well, one of the real misleading comments about this is they say, well, AI will become like electricity. It will be everywhere, ubiquitous and usable. But electricity is one single constant thing. It's an electromagnetic wave, and we can apply energy and all that, right? That's not what AI is. It's not a singular thing that you simply plug into and get good results. It's just the opposite. It's something that's very complicated, needs to be dynamic, needs to learn, needs to get new and better information. There are inherent biases, as we're seeing. And so to say that artificial intelligence will spread generally and, essentially, the robot armies are coming, that I think is a long way off, and I don't think it can be achieved given the current models that are being used today. And so what I'm saying is, detail matters, but lack of detail also matters. Now, here's a project going on where people are trying to predict, let's say, the next frame of a video. And the current models basically essentially try to predict it pixel by pixel. Well, what's the next pixel going to be? And so those pictures are very complicated. There's a lot of data there. But you and I know that we don't need to do that in real life to predict what's happening next. If you look at any frame of any image, there are many things that aren't changing and many things that your brain immediately filters out saying, well, that's unimportant, that matters, that's important. So for instance, a very simple example of you're trying to catch a ball, right? Well, there's a very complicated equation that your brain is doing to catch that ball in terms of gravitational force, acceleration, all of those things, but it's ignoring the background, right? It's ignoring the things that are happening around it because that's unimportant for the task of catching the ball. And I think that analogy applies directly to what's happening with artificial intelligence because we're assuming everything matters. And if everything matters, then let's predict what's going to happen next. That, because we have processing power, we think that can scale, that can't scale. And I think that the problem is we have to monitor what's relevant, really understand what matters, like that example of catching the ball, understand what really matters, filtering out the rest, and having a dynamic and very applicable model. And that's a different approach than what we're seeing today. So how do we solve this? So there's some very interesting work that Douglas Hofstadter has done, and he looks at, well, how do humans really learn? And his thesis, and I embrace this, is that we really learn by simulating, And our brain works by analogy. We've seen this before. How does it apply here? And that's the essence of how we function and learn. And so think of a simple example. You want to wash your hands, right? Well, okay. So you go to a bathroom you've never been in before. Well, you know how to work the sink, you know how to work the faucets, you know how to work the soap and all those things, but you've never seen those specific things before, right? So that data on the one hand is all new, but on the other hand, you have this frame of simulation and analogy that enables you to function very seamlessly. And that's really how we think and function generally. And I think that this approach then leads to what Hofstadter defines as intelligence, which is predicting the future. And I also embrace that. Even as an investor, we think, well, whatever you're doing, if you can't predict the future, you won't be an effective investor. And so taking this analogous knowledge, this referential knowledge, and then understanding what should happen next, what could happen next, what's most likely, that's a real form of intelligence. And I'm embracing that as part of the solution to a more appropriate and applicable artificial intelligence. And so one of the things that we also understand is we think about, go back to that pixel example, connect all the dots and then predict the future. Well, that's not how the world works as well, right? We work with incomplete information. We work with, fragments. We put those fragments together. We arrange simulations in our mind. We arrange referential analogies in our mind. And then with that, we're able to understand a situation, deal with a situation, and then predict the situation. That's a more applicable model for artificial intelligence in general. And so what really matters is understanding kind of what the possibilities are and then the relevance for those possibilities. Instead of saying, here's all the things that are possible, let's predict that. Well, if that doesn't work, let's predict something else. If that doesn't work, let's predict something else. That becomes massively inefficient if you try to apply that more generally, right? And so the real point here is that prediction equals intelligence. And I'm embracing what Hofstadter was saying. So we now have to be able to understand to predict. Well, relevance is the essence of understanding how to predict. So we first have to filter what is truly relevant. Let's manipulate that. Let's understand that. Let's get better data for that. And then with that, we can generate a prediction, which is essentially intelligence. And that's the foundation of artificial intelligence as we should develop it today. So one of the things I want to talk about, I call it cognitive architecture, which is different from neural networks. So cognitive architecture is really more like how the brain works. And this is a fascinating thing to really study, because one of the things that the brain does is it has, these dendrites physically that perceive a lot of input and a lot of information, but then it collects that and configures it to see, well, what is useful and what's not. And this is where layering comes in. So the brain naturally layers, much like artificial intelligence programs layer, right? So the brain naturally layers and naturally understands priorities and essentially creates an algorithm within each neural, an algorithm that says, well, this is important, this isn't, this has less importance, et cetera. And it's already doing that configuration. Then the next thing that it does is it understands the signals it receives. Then it processes, well, what could I do? They call it an action potential within neuroscience. So what's the action potential that this neuron is now perceiving? And here's the real interesting thing. Then that neuron itself within the axon, which is part of the biological structure, the axon will then process that locally. And this is the real difference between human, we'll call it networks, and the brain itself. The brain can do this processing locally. We don't have an ability to do that yet. But it does that processing, and then it figures out the most appropriate action very efficiently. And that's something that essentially what it does, and this is the analogy that I'm referring to, is it takes its inputs, it quickly figures out what matters, what's relevant, how to weight those relevancies, then how to process them, and then how to then predict an action. And that is really the solution to how we think about artificial intelligence more appropriately. While we have layers, the thing that we really need to understand is how these things interconnect and how we can then learn. Because one of the things that AI, the models AI works with, and we'll get into that, one of the things AI does is it layers, it processes, it spits out an answer, then it keeps going. But it's not really referencing additional data. It's not really learning more, as let's say, as effectively as I think we can develop a model to do. And so what the brain does that artificial intelligence doesn't do is, we call it, it gains information. It learns, but it also keeps that reference and it transfers that knowledge, but it retains the knowledge that it's transferred. So it builds up, honestly, exponentially. And here's the example of how it doesn't work in real life, because we have, let's say, deep thought processing how to play chess. Well, it grinds through how to play chess, and it grinds through big data, and it does analogy upon analogy upon analogy, and then it figures out how to make a lot of moves and then how to make the best move, and it does that very quickly. But then it forgets that knowledge as soon as it has to learn how to play the game Go, right? It doesn't have referential knowledge. It has to relearn a new task, but there's no reference, there's no sharing. Systems don't work that way, and that's a big shortcoming for how models work today, and a solution that's needed to overcome that. So when we think about applying energy and efficiency, I'm saying the megawatts versus watts, right? So the problem is that we look at learning right now in our models as if it's just a lot of data crunched through with a lot of processing, and we get an output. We get an output that a human being really can't produce. So that's great in a well-defined problem like, let's say, playing chess. So, a big blue can look at a potential move and understand there are 7 million moves I can make, and he can make, and I'll pick the best one. And a human being really can't process that at some point. But that's a well-defined problem, and it works in that very well-defined area, but that's not generally applicable, right? And the world we live in is dynamic. It has very specific applications. Big data, trial and error just won't work effectively in these environments. And we're seeing that with the tools we use, and we've developed our machine learning tools. We look at very specific situations and understand that it's dynamic, it's specific, it leads to a much better understanding. And my point is, bigger is not better. So let's collect all this data from all the people who use all these services, and then let's just come up with some conclusion. Anyone who's been exposed to the outputs from this big data approach, you understand how most of the time the results are kind of absurd, right? Because they just look at an historical pattern that isn't nuanced and dynamic enough, for your application. And that's really the point, that large data sets really are not the story. That's not what's really going on. In our experience, where we're looking at market movements and trying to develop algorithms that can then trade profitably on that, we understand data sets need to be narrow, very relevant, dynamic, understand how to update themselves, how to then understand priorities, and be much more effective. Just big data applied more generally ultimately doesn't create a lot of value. And so quality matters. So what the real point here is, just like the way the brain works, it initially looks at all this data, all its input. It figures out immediately, well, what's important, what's not. How do I then understand the relevance? How do I then prioritize, then process, and then predict an action? That's done with a very small amount of data, dynamic, and very focused. And a great example is language, human language, right? So this is based on work that Jeffrey Waddimal has done at both Harvard and MIT, and he's worked with Noam Chomsky at MIT and Steven Pinker at Harvard, where they've looked at language, right? So one of the things that we all understand is, the miraculous development of human language, right? Maybe the single thing that distinguishes us from all other creatures, as Noam Chomsky would say. But we seem to have an infrastructure that can take very incomplete data and be able to develop a language capability. I mean, it's really fascinating. And those of us who've struggled to learn another language later in life, you understand the real struggle with trying to learn that. And in my case, trying to learn Mandarin. And then you realize, well, any 5-year-old can learn Mandarin. Now, that's fascinating, right? So any child from anywhere in the world can go anywhere else and learn that local language very quickly. That's from incomplete data. It's using referential analysis. It's using analogies. It's filling in the blanks. It's connecting dots. And there's a great form of artificial intelligence that's going on there. And I think and Jeffrey Waddimal is doing this. I think you can apply that directly to real-time artificial intelligence and artificial intelligence programs now. That is a very, very interesting development. And that's that's our approach as well. We embrace this completely. So the better artificial intelligence solution, right? So large data models, they can't transfer data, they can't transfer learning, they can't transfer relevance and predictability. That's a big deal, right? So if you try to learn by trial and error, or you try to learn by reinforcement, do this, it works, do this, it doesn't work, that doesn't really scale. And think about, again, we talked about language earlier, but think about just when you want to jump over something, right? Well, immediately you process the relevant information, and you can process your capabilities, and you can understand right away whether or not realistically you can jump over that thing. Whether or not you're on Instagram, that's another story. But a computer can't do that, right? It sort of has to do all this analysis and all this processing and all this like trial and error, right? So, if I do that, I don't make it. If I do this, I do make it, right? Well, that doesn't scale, doesn't work in real life, right? And so we have to understand that a model that's got questionability and practicality. And I really think, if we're going to disperse the artificial intelligence generally, if we're going to use it as a very effective tool in real time, we really have to understand this sort of natural learning process and make it more applicable. So the point is, it's real learning, it's referential learning, it's learning by analogy, it's sharing data, it's building on data, it's being able to use a foundational learning process. And with that, we get better data sets, we get more focused data, more information, a better dynamic approach. That dynamism leads to more effective results, and then we go on and on with smaller data sets, smaller bits of processing, more effective and more applicable. So to summarize, we're saying that the approach with big data, trial and error, all of that doesn't really work. It doesn't lead to what we're calling common sense. Common sense is the ability to predict what really ought to be happening next. And with that, the solution is smaller, higher quality data, smaller data sets, a dynamic nature to those data sets, learning, referential learning, analogy, all of these things which are available. And these are tools that we are using where we're being more effective with machine learning and artificial intelligence. And we're really relying on cognitive architecture, real cognitive architecture, not some marketing term that's called neural networks, which really doesn't do anything to mimic a true neural network. We're not there. But understanding cognitive architecture and learning language is probably the best example of that cognitive architecture being very effective and essentially implementing the analogies to those structures. And so using less energy, more applicability, more relevance, and that's a better solution for artificial intelligence. These are the models that we are using, and this is the work and the research that we are espousing.